Okay, so I promised that we would get to a point where we can use KSP to predict solubility instead of having to memorize a table or interpret a table. And so let's do that with an example here where we have essentially two beakers. One beaker has 150 milliliters of this lead nitrate solution at this concentration, and a second beaker has 100 milliliters of NaCl or sodium chloride solution. And we're going to mix these beakers together. That's what the problem is saying. So we're going to have one new beaker where these two things are mixed, and we want to evaluate if a precipitate's going to form at all. So we get a chunk of solid that we'll be able to. So I like to draw things. What we have in our new solution here, once we mix them, are 4 different ions, and we have a new volume of about a quarter liter. And we want to know, are any combination of these things going to form a chunk of solid down here at the bottom of our system? That's the question. And so we don't have to do this, but I think it's helpful if you have a little bit of chemical intuition. You know that sodium and nitrates don't typically form solids. And so that will save us about half of our time if we just say, well, anything with these two species connected to it are probably not going to be the issue. And that makes sense because we had a solution of lead nitrate to begin with, which was a solution of it. And so a combination of these two isn't going to do anything. That's probably going to be true then for sodium and nitrate. We could look up KSPs for that really quickly and make an assertion and say, yeah, actually KSP is huge for this, so that's not a big deal either. So that's our first. That really, gets us to the point of, well, then what would form if sodium and nitrate don't do anything together? Then it becomes sort of natural to consider this system first. What is lead and chloride going to? Well, to consider that, we just need the KSP for that solubility expression. So lead chloride is comprised of the two ions here. KSP I can just look up online or in the back of the book, and we get something that's got a pretty small KSP. It's not the smallest I've ever seen, but it's not that big. And so the question is, this is our sort of hypothesis, right? Well, we know that lead and nitrate are soluble together because that was in the original beaker. We know that sodium and chloride are soluble together because of this other beaker. And we are making an assertion that sodium and nitrate together are probably also soluble. So our first guess is that if something's going to form, it's going to be lead chloride. But that's still an if. And so we need to figure out with these specific concentrations, would we get a precipitate? So we know the KSP expression for this system is this, and it has to equal 1.2 times 10 to the minus 5, but we have actual values for these things, right, that are coming from the real conditions of the system. And so just like we'd done in the past with equilibrium ages ago, where we computed Q, which is the reaction quotient, and then compared that to the equilibrium concentrations, we're going to do the exact same thing. So we're just going to figure out, okay, well, what is the product of lead concentration times chloride concentration in the new mixture? And is that greater or smaller than the equilibrium condition? And that will tell us whether or not we're seeing a precipitate. So we just need to figure out how much of these individual ions we have in solution. And so you could write these out as actual dissolution reactions, right? 0.1 molar of lead nitrate breaks apart into 1 of the lead ions and 2 of the nitrates. So that's important to consider. And similarly, sodium chloride is going to break up into equal parts. So I can just figure out the moles of lead in this solution simply because I know that if I have 0.1 molar or moles per liter of the actual salt, then it's a 1-to-1 dissolution. So that means I also have 0.1 moles of the lead 2 plus when it breaks apart per liter, but I only have 0.15 liters, so I would multiply that. That gives me the moles. And then I want to divide this by what my actual new solution volume is, which in this case is our 0.25 molar. So divide by 0.25 molar. Those liters go away, and now we're back in units of moles per liter, or molarity of the lead. So that will be the value that I can punch in for my lead concentration here. So we can do the same thing for chloride. and that looks something like this. So 0.2 moles chloride per liter. I only have 0.1 liters of it, so that gives me moles of chloride. Then I redivide that by the new solution volume. That gives me the molarity of chloride in this new solution. So now we have molarity of lead and chloride. So both of those values then can get pushed into this expression, and we'll solve this for not K, because K is a constant, but we'll solve it for essentially Q. And it's important to note that this is, for all intents and purposes, Q, but it gets its own special name called the ion product, or IP, which I will say is practically the same as Q. It's identical in concept. And so we're going to compute the ion product here, which is going to be the 6 times 10 to the minus 2 times 8 times 10 to the minus 2 squared, and see what that value gives us. And the value here is 3.8 times 10 to the minus 4. And if we go, I'll just make some room up here. In this case, we want to compare it to our KSP, and so it shows that IP, which we'll just say is Q, that is about 1 order of magnitude greater than what our KSP was. So what does that mean for where our equilibrium lies? Well, it means that we have more ions in solution, right, than what K would dictate at equilibrium. And if we have too many of these lead and chloride ions so that it exceeds K, then that means the solid will form, and we will end up with something that forms on the bottom of the solution.